With standing waves, we saw our first example of quantization, and we will see that this concept was at the heart of the revolution that happened in physics at the beginning of the 20th century. The idea that energy must be quantized was first introduced by Max Planck in order to solve the ultraviolet catastrophe, and was extended into other areas by other physicists shortly thereafter. What is this ultraviolet catastrophe? It had to do with a phenomenon called black body radiation. What is a black body? A black body is an object that emits light of all wavelengths. The sun is such an object, and here in yellow we see the way the light emitted from the sun is distributed from UV through infrared wavelengths, as compared with a black body here on Earth, like a hot piece of metal, which is shown in blue. We can see that observations for the two objects are well correlated. We can also see that intensity is greatest in the visible portion of the spectrum, which then slopes down on either side, steeply to the left and more gradually to the right. Physicists had a mathematical model that could predict the intensities for each frequency at varying temperatures. But the problem was that the math, which was based on classical theory, did not suggest a steep downward slope in the UV portion. It predicted that the intensity becomes infinitely large with decreasing wavelength. This is absurd, because we know from observations that normal everyday objects do not emit enormous amounts of UV radiation. If they did, we would be in big trouble. But Max Planck solved this problem by assuming that the vibrating atoms in the hot metal that generate the radiation, instead of having any possible vibrational energy, can only have particular energies. That is, their vibrational energies are quantized. Thus, he developed this expression for black body radiation, where energy is equal to n, which can be any integer, times a new term he developed called Planck's constant, times the frequency of radiation. This ad hoc constant and the application of quantization allowed for the math to accurately predict the true distribution of black body radiation, which meant that it was more than a mathematical fluke, but a clue as to the true nature of reality. And the fact that Planck's constant is so incredibly small explains why the notion of quantization of energy had not cropped up before. This was the first time quantization solved such a big problem in physics. But it wouldn't be the last one, once Einstein got into the mix. And physics was never the same, having taken its first step down the path that would eventually be coined the quantum revolution.